Okay, so we're going to go over, there were, let's see, about 15 questions on this. And for those of you that are at home, just make sure that this gets turned in sometime this week. You could fix anything that you got wrong if you need to, but I'll give you some points for completing it. The main reason I added this in is because there just wasn't a lot of questions in your textbook about this topic. And sometimes there's some questions that pop up in the AP test on this. And this assignment got into pretty much everything possible that aspect you could be asked about these potential energy functions. So remember, I posted a PDF version of this that I copied with numbers beside them since they weren't numbered on the actual one. But if you did complete all or most of it and entered a value and hit check, you were able to see what you got wrong and what you didn't. But not all of them gave you a solution, so that's why I'm going to go through every one. All right. Main idea, though, is that if we give you a potential energy function of position like this one, a u of x function, basically, if we take, this is section 7.4, we first ran into this, if we take the negative derivative of that, what does it give you? You remember, Spencer? The negative derivative of a potential energy function like this gives us the what at any given moment. You recall? It was the force acting upon it. Okay, and not the work, but the force is involved with the work. So you could like take it that, but straight up, if you just take the not just regular derivative, negative derivative of this. So take the derivative like you would normally of whatever rules apply, and this is still just a polynomial function in the end. So basically, it's mostly power rule, right? And just make your derivative negative. You flip its sign, and that will give you and tell us the force at any given moment acting upon something that is defined by this function. So this particular function is both fully given as a formula and is graphed for us as well. So the first question is, what is the value of this potential function at 0? Or initially, where the graph starts, right? At a position is 0. So that's a pretty easy question there. All we got to do is plug in and evaluate it at 0. Okay, so going over to just my work, that's exactly what I did. U of 0, plug it in for x, evaluate it, and we got 6 joules. But in coming questions, that's important because in a little bit, one of the following questions basically tells us that it was released from rest. Whatever this object was that follows this function, it was released from rest. And if that, so at position 0, it wasn't moving. So if we have, remember, conservation is all intertwined with this. If I got 6 joules at this position of potential and it's not moving, the total energy is 6, right? Because if it's not moving, it has no kinetic. And if we follow conservation law throughout it, then at any given moment, if we started with 6 total, at any given moment, we have to have how much? 6 total, right? It just might be divvied up between potential and kinetic differently, but it should still total 6 as long as we're undergoing only conservative forces. All right, so in number 2, it says, what are the values of positions x1 and x2 right here and right here? Now, to do this, we need to use that negative derivative. Because x1 and x2 are special points. Look at, here's where you got to focus on the graph. And this one's not hard to do, but it might be hard to know what to do without seeing something like it done first, because it might not jump out at you. X1 and x2 from last week we defined as equilibrium positions. Equilibrium positions are positions where at that moment the force on the object is equal to what? At equal 0, right? At equilibrium for those moments. How do we know that? Because they're peaks and valleys of the graph. Remember, if the negative derivative of the function is the force acting on it. And we remember what derivatives are graphically. They're tangent lines to the curve, right? So a tangent line to a peak or valley, crest or trough, whatever you want to call them, is a flat line, right? So that means the force is 0 there. And we could use that to our advantage to answer this question. So number one thing, we need to take the derivative of that function. And it's just using the power rule and the polynomial functions, so that should be a fairly basic one from calc, but here's all the work for it if you need to see it. All right. When I do that, I set it equal to 0, right? So what we see after we take the derivative, when it comes down to it, is that this ends up being a quadratic function, all right? Because there's a squared in it, right? What kind of graphs, this is going to be important in a later question, but I'm going to ask it now. What kind of graphs do quadratic functions make? Parabolic, exactly. So that's why we get two answers. And those two answers must represent x1 and x2, because they're the only positions on the given graph that we took the derivative of that were equal to 0, right? So that's not a coincidence that we got the two answers right there. They're x equal x1. The lower one will be the leftmost one, which was the position x1. I redrew the graph up here in the solutions. And x2 is the 2.82, the one more to the right. Does that make sense? And that was all because of the fact that we knew they were equilibrium positions. And we, at this point, should know that if we take the negative derivative, which I did right there, equal to 0 at equilibrium positions. All right, now that we're going to have those equilibrium positions, there's going to be some questions of figuring out some other stuff about them. In number 3, it wants to know how much potential energy we have at x1. As long as we got it, this is an easy one. We just evaluate the given function at that position because it's a potential energy function. The original given one, we plug in 1.18 and we get 0.911 joules, which leads us into another number 4 and the conservation fact I mentioned earlier. Number 4 says if the object was initially released from rest, so that's where they finally tell us that. So remember, initially we already found potential at u of 0 was 6, right? And that's why I said earlier that that must mean if it was from rest, we had 6 joules to begin with. So anywhere else at any other position, this one just happens to be asking for position x1, the potential plus the kinetic has to total 6, right? And it's asking how fast we're moving as we pass through this position. So that clearly means we have some kinetic there, right? And we just found in number 3 the potential at that position. So that potential plus the kinetic has to total 6. Does that make sense? All right. And the kinetic we don't have, but we have a formula for it, 1/2 mv squared, right? And m was given in the original information as 0.5 kilograms. So our only unknown is simply v. We solve this formula for v, and we get about 4.51 meters per second as it passes through that position. And that just confirms the basic idea of what we already started, like we basically started this chapter with. As we lose potential, we gain kinetic, and vice versa. As we lose, as long as everything's being conserved, then as we gain kinetic, we would, or as we lose kinetic, we would gain potential again, like other parts of this graph show. Any questions so far? Okay. So number 5. How much potential energy do we have at x2? So we just evaluate it, the given function at 2.82 that we found in earlier, x2, and we get 3.09 joules. So we get question number 6, which is really just like number 4, but at this new position, x2. So the total to begin with still has to be 6. We just found u at 2.82 is 3.09, so we add that to whatever kinetic energy formula, 1/2 mv squared, solve for v again. And at this position, we have 3.41 meters per second. Number 7 should be a pretty simple question as long as you remember from last week. Which position of these two already defined equilibrium positions, x1 or x2, is stable equilibrium? Which one is it? Which one of those would be considered stable equilibrium? You remember what that meant? X1, good. It's a valley. So we don't know, we weren't told physically what made this potential energy function, right? We were just saying, here's a function, some object that's 0.5 kilograms is following, its energy is following this function mathematically. We don't know what it really is, but I think the best way to imagine it, for simplicity, for a stable and unstable equilibrium, imagine that it's literally something like the roller skate park guy, or like imagine like it's a roller coaster track, because there's gains and losses of potential energy. There's a track moving up and down as we travel, maybe horizontally, right? Like this. So if you think of this just like a track, it's easy to understand why this is stable in equilibrium. If we took like a marble or something, or a ball bearing, and this was a track, and we were at a stable equilibrium position, if I pushed it to the right or pushed it to the left, it would come back to the stable equilibrium position, right? That's why it's stable. But if I set a ball at the peak of a hill, like this one, at position X2, if I pushed it to the right or to the left, it would fall off and wouldn't come back, would it? So that's why they're both equilibrium positions, because the force would be zero. But this one's stable because if you displaced it from it, it wants to come back. This one's unstable because if you displaced it from it, it would fall off and wouldn't naturally want to come back without some work being done by a non-conservative force. All right, number 8. How fast is the particle moving when its potential energy is 0? Well, if its potential 0, then that must mean all of it transferred to kinetic, right? Because it still has to stay 6. So we just set kinetic 1/2 mv squared equal to 6 for that reason. And therefore, the fastest this thing could go, possibly somewhere, is 4.9. It can never go any faster unless it was given an extra push by some non-conservative force. All right. All right, number 9. If x3, that position right here on the original graph, if that's exactly half of x1, how fast is a particle as it passes through position x3? All right, so x1 we had, so if we half it, we know position x3 is 0.59. Then we evaluate the potential. So this is like a lot of the early problems, just with another position. We evaluate the potential at that using the function. We get 1.98 joules. And we, for the third time now, say that 6 is the total, and both have to add up to that. So 1.98 plus 1/2 mv squared have to total 6. V, again, is the only unknown, and we get 4 meters per second for that to happen at that position. Still good? Yes. Okay. Now, the next part is the one that's, might be the trickiest until you really think about it and think about Newton's second law. But I did give that hint last week. To think about how force, since we could get the force by taking that negative derivative, and force and acceleration, we learned in the past, is related through Newton's second law. F net equals ma, right? So with that in mind, number 10 asks us to sketch up the graph of a particle's acceleration as a function of x. Indicate the positions x1 and x2 that were on the original graph on this graph. Describe your graph and the area provided. Okay, so first what we got to do is actually just go back to some work we already did. In number 2, we took the negative derivative, right? And we got this, and we used it then to set it equal to 0. We don't have to do that now. I just need the force function. So going back to taking that negative derivative, we got this. But what I'm also going to do now is expand it. And all I mean by that, if you're unfamiliar with that mathematical term of expanding, is I'm actually going to FOIL this, because this quantity is squared, right? If I FOIL that and distribute the 3 and combine like terms, I get a quadratic function in standard form. If you recall somewhere in your past math careers, that standard quadratic form means everything is on one side, everything's expanded out, which I did, and it's in descending order. What that means is if there's a squared term, which if it's quadratic there has to be, it's first, right? Then we put in order the first power, x to the first power term, and then the constant, right? The reason why I did that, because more than likely, most of us probably learned to graph in somewhere in Algebra 2 quadratics from standard form, at least features of it. There were other forms, all right? Actually, this is a form in itself right here. But this one allows me and shows me one of the most important features of this general graph that we have to make. If you remember somewhere back to, well, let me get there because hold off on what I was just going to say, because actually for the moment, this is a force function. I had to graph acceleration, right? So this is the expanded force function, but because of Newton's second law, I could set that equal to m times the acceleration, which also is a function of x. And we were told that because we're asked to graph it as a function of x. So the only reason I set this equal to ma is because of Newton's second law, which should be legal, right? And we know the mass. So if I want the acceleration function, and I already have the force function, I could divide the mass that was known, 0.5 kilograms, to the other side, right? Make sense? And if I do that, especially since I have it in expanded form, I could divide every term by 0.5, right? So that's what I did here. If I divide every term by 0.5, it doesn't change the fact that it's quadratic, but it changes the coefficients, right? So at this point, this is where we could think of some basic features of a quadratic. Starting with the fact that this would be an upward opening parabola. If it's quadratic, it's got to be a parabola, right? Why do I know it's upward opening? Parabolas could open upward or downward, right? The leading term, this is something you got to remember from past math, which I'm sure we learned somewhere. If the leading term, the 6 there, the leading coefficient in standard form, if it is positive, it opens upward. All right? And we already know that from past questions that position x1 and x2 are equilibrium points. Remember, equilibrium points are where the force equals what? Nope. 0. All right? Equilibrium points are where the force equals 0. And since through Newton's second law, force is directly proportional to acceleration, if the force equals 0, the acceleration has to equal what at those moments? 0. So we know the graph has to open upward because of that being positive, and we know that at these positions, x1 and x2 have to be possible and at 0, which is why the graph passes through them on this axis. So those two things allow us to draw a general graph. A parabola that opens upward that passes through x1 and x2 on the x-axis, or the 0 position for A. Does that make sense? This is the only way you could draw it to make those things occur. So that means part of my graph is in the negatives for acceleration, which is completely okay, right? And there's going to be a question about that in number 11. But are we okay with how I got that graph? Because that was a little tricky. Okay. And it just had to be the trend, and the main thing is your graph had to show x1 and x2. But again, for those of you at home too, the only way to draw a parabola that goes through x1 and x2 that we know are equilibrium, where f and a are 0, would have to be drawn like this, where part of it loops back through in the negative, or quadrant 4, where accelerations are negative. All right, so if you didn't get number 10, you probably couldn't get number 11. But number 11 asks, at what value of x does the particle experience its greatest negative acceleration? So if we got the general graph, we could clearly see right here, right? And this is another thing that, if not that parabolas and quadratic graphing are difficult whatsoever, but a lot of us might not have had to do this for a while, or since you did it in Algebra 2, possibly. And sometimes it's easy to forget even simple things from back then. But if we define it here, you'll remember a term mathematically, that's called the vertex of the parabola. It's the turning point. Okay? And this is another reason it's nice to have this formula in standard quadratic form, because the vertex formula to figure out where it is, at least the horizontal component of where it is, x, and that's what they're asking about, at what value x, right? So we want to find the x value at the vertex, and that was a old math formula somewhere I know everybody's learned, just may not remember it, is x equals negative b over 2a, where b is this coefficient and a is this coefficient. Just how, like, when we have to use the quadratic formula, that this is a, b, and c, right? All right, so that might have been, even if you got the graph, it might have been tricky remembering this formula and knowing it's there. But if we do, that gives us the x position, and that's exactly what's being asked in number 11. What value of x does the particle experience its greatest negative acceleration? It's at that vertex. So if we just go back to that formula, pull out those coefficients, remember to take signs that come before them with them, pop it into the vertex formula for the x value, and we get exactly 2. So at that position, we'll have our greatest negative acceleration. We good on that one? Okay. A few more left. What is the value in number 12 of its potential energy at this position? All right. So that's easy once you get it. Just you couldn't answer 12 if you didn't get number 13 or number 11, excuse me. But we just evaluate the function that was originally given. The potential energy function evaluated at 2 is 2 joules. And now we're kind of being back to asking some of the same kind of questions from earlier. In number 13, how much kinetic energy does it have there? Again, remember U of 0 is 6. Solve for K, the kinetic energy, and that's 6 minus 2, so it would have 4 joules there based on using conservation. 14, what force is being exerted at this position? So we go to the force function we derived already. I went back to the one I derived in number 10 that I already had in this form. It doesn't matter what form it was in as long as you evaluate it at that position. That must mean a force of negative 2 newtons is acting on it. And then it says what's the acceleration at this point. I have it done 2 different ways, but probably both of them are easy, but I did them both 2 different ways just to show it doesn't matter. We already in number 10 figured out the acceleration function, right? So if I evaluate the acceleration function at 2, I get negative 4. Or we could again use Newton's second law. If we already know from number 14 the force is negative 2, and divide it by m, mass, that must mean the acceleration at 2 is just negative 2 divided by 0.5 and negative 4 meters per second squared. Doesn't really matter which way you do it. They all come from the same idea. Just wanted to show that you could do it either way. All right, but that's a pretty good situation that asks you every aspect you could pretty much be asked about these potential energy functions. And again, there's a couple problems that you're going to get into this a little bit, but not as detailed as this thing did. Any questions, Spencer? Any of you guys at home, if you have questions, if something didn't make sense, just make sure when I see you guys tomorrow, ask immediately before we go on to doing the lab tomorrow. All right, so I'm going to, I don't have it posted yet, but just in a minute, I'm going to post the final problems on Classroom for the remainder of the chapter. So the rest of today in class, we're going to have time to continue those. And then for you guys at home, we are going to do a lab tomorrow, and we're going to flip-flop. You guys are going to do the lab tomorrow, and then we'll flip-flop with the blue group. They'll do it on, or Spencer will do it, I only have one, on Wednesday. The day you are not doing work over the next 2 days is just going to be time for you guys to complete all the chapter problems. I want all the chapter problems attempted by Thursday, and we'll go over questions on Thursday. But we will not have the test until next Tuesday. You guys are off Monday. Friday's a short period day. Oh, yes, good question. The test will be on this marking period, because officially the marking period is not over until the 20th. So it'll be it and the homework that goes along with it will be the thing on this marking period. The lab will go on this one as well. So that really puts us at like 40, 60 homework. That puts us as at least like 80 more points, something like that, if not more. But also, guys at home, consider you guys still have to turn in, which I forgot to collect last week, you guys all still have to turn in the old homeworks. And that's like a guaranteed approximately 60 points, as long as you did them. So if your grade's not where you like it to be, there's a ton of more points going in this last few days.